Hello guys, my name is Sanil. In this video, we're going to discuss about trees, which is a concept from the data structures. Uh, Later we use in our data subject also. And we know the tree definition. The AP data structure is a hierarchical representation of data. That means we're representing our data in the form of tree. We know that tree has some branches. So in these branches are called as child limbs. And the branches have some leaves. So by representing tree, we can easily understand the trees in the data structures. So trees are widely used in computer science for efficient data storage and manipulation and retrieval. So going to the topic, we have some terminologies and properties of the trees. For every concept, we have some terminologies. So the tree data structures also have some terminologies and properties, which is very common in any concept. So representing we can learn these trees by representing our daily life trees. So tree terminologies and properties. So first one is we start with root, which is the topmost node in the tree with no parent. That means it is the topmost of the tree. And the second one is the leaf. Leaf is nothing but opposite of the root node. That means it's the least node of the tree. In other words, we say like that, which has no parent, which has no child. And other terminology is subtree. It is a smaller tree of the large tree. It is a subpart. So this is the terminologies of the uh, trees and properties of the trees. So there are some types of trees like binary tree, decision tree, and balance tree. Binary tree is nothing but with the parent which have two nodes. It must two nodes, nothing but it means two or three or four. Not at least it is at most two. And second type of tree is decision tree. Uh, it is used in decision making models like algorithms also. And third one is balance trees. A cell balance tree structure use it for efficient data storage and retrieval, which is more important for many algorithms. We can learn more in this video about these types of trees and techniques. So every concept and every data type, every have some advantages. So there are some advantages of trees, not so, but so many advantages of trees. So first one is efficient data organization. Uh, you by taking some example like data, we can arrange the data in the form of trees. We can divide it into parts like root node, leaf node, subtree, and we can arrange the data in the form of trees. So like uh, uh, files in our files we have sub files folder. We have folder in that folder we have many files like that. We can do with same trees. So efficient data organization, that means tree provides a logical and hierarchical way to store and access data and easier searching and sorting. Uh, for example, uh, take a folder. In that folder, we have sub files. When we searching for some file, we can specify which folder. That is very easy for searching. So, uh, trees based algorithm like binary search and traversals enable efficient searching and sorting and flexible and adaptable. Uh, because it is adaptable. When we use something thoroughly, it can adapt us. So three concepts also we can adapt us very easy. But it also has some complex relationship also because every good for us may have some complex. So this is the advantages of trees. So some graph. So trees have some techniques like graph traversal techniques. There are two types of techniques. There are depth first search, nothing but we can commonly call as DFS, and breadth first search, uh, many are called as DFS. And the main difference between DFS and DFS is depth first search is going in the depth way, nothing but deep. And breadth first search going by in the form of level wise. It can divide in level 0, level 1, level 2. So this is the main difference. And another difference is we can talk earlier in this lecture. So this is the two types of techniques. And by taking some example, we know the exact difference between these two techniques. First, we go with DFS. Some terminology and properties of DFS or root. It can start at root, nothing but begin the search at the root node of the graph or tree. It is either graph or tree, it starts at root and explore deeper. Nothing but we can go deeper and deeper. Here we see, here is a A. It go in the D and G. So it could, this technique take us to deep. And when we reaching to the dead node, so it can have the most important technique, a property called backtrack. In the DFS, backtracking is there. So we return the most recent node with unvisited neighbor and continue the search. So this is the depth first search, and we can go to some example. So here we see there are some numbers like 0, 1, 2, and 3, 4, 5, 6. The 0 is the root node, and 1, 3, 4, 5 is the subtree, and 2, 6 also subtree. And the 3, 4, 5 is the leaf nodes, which have no child nodes, which are called the leaf nodes. So it explores like first it comes to a 0, 0, and in the stack, we know that uh, trees, DFS use the stack. So when we start with root node 0, you can explore the deep. First, you can go to the left side and you can explore 1, after 2, left, right. And after exploring 1, it will go to the deeper 3, 4, 5. 3, 4, 5. So after that, it can backtrack. So this is the dead node. After it can backtrack to 1 and it go to 4. After it backtrack. So at earlier till that backtrack is the most important property of the DFA. So by after complete of the left, it can go to the right side. So it can print like 0, 1, 3, 4, 5, and 2 and 6. So this is the depth first search. And breadth first search. This is the second type of a we have to do.